Hello there, welcome to a presentation on numerical solutions to first order differential equations. My name is Charles Waswanemsipa. This is an introductory lecture to numerical methods of solving differential equations. By the end of this presentation, you must be able to explain why do numerical solutions to differential equations and be at least familiar with the one formula or procedure we're going to use to find solutions to numerical differential equations. So as motivation, let's start by looking at the following. In our first calculus course, we saw problems which could lead to this kind of differential equations, and through the introduction of differential equations, we saw that this is a kind of problem which we could do by direct integration. In this case here, we would say y, the solution to this differential equation, is the integral of x e to the power x squared dx. And we know that we can integrate this problem by doing substitution, or you can sort of go on transforming this function in such a way that it looks like a derivative under the integral sign. In this way, by simply multiplying this by 1, which is a 2 over 2 x e to the power x squared dx. By so doing, you can see that here, so we've created the derivative of the argument, which is x squared. Then filtering out half, we're left here with 2x as a derivative of the argument of e to the power x squared dx. And then integrating here, we know that this is going to come up as e to the power x squared over 2 plus c. So we can say now here we have solved this differential equation using analytic methods, and then if we want, we can find a particular solution and determine our c. But on the other hand, if we look at this kind of a problem, it's not a problem where we can say y is equals to integral of e to the power of x squared, because we cannot do something similar to what we did before to integrate this problem. But in the case maybe we wanted to integrate a function like this on an interval, let's say from 0 to 1, e to the power of x squared dx, we know that this function, let's say f of x equals to e to the power of x, can be graphed on a system of coordinates as follows. You can graph it this way. So if you wanted to integrate it here, you would basically be talking about the area between 0 and 1, which is the shaded area here. So in that case, we would wanted to evaluate the current this way. We know what to do here. We would do numerical methods. In this case, we're talking of what we call trapezium rule. You would also do Simpson's rule, and so on, other methods. So this takes us to basically thinking of that we might also find differential equations which we cannot solve analytically but numerically. In this case, we can look at the following example which we have got here. Differential equation is as it is: dy dx is equal to y squared minus x squared. Is a differential equation. And then what we can see here is none of the equations which we saw before, like separable, homogeneous, is none of those. And then what actually we see here, we cannot solve this equation. We cannot find y, a function of x, using analytic methods, but we can resort to numerical methods. But in this case, we need an approach and kind of understanding and motivation of the approach we're going to follow. But what we understand now, if we solve this equation and put it as y is equal to f of x, then we can think of the situation that this function, which is a solution to differential equation, can be plotted on a system of coordinates. In this case, it can be a graph, for example, of this nature. At this point, I would like to point out again that numerical methods for solving differential equations are normally used for getting approximations of the solution over a small interval. So we'll be doing this over a small interval. For example, we can say 0 to 1 or 0 to half, whichever case might be. So now, if we think of the fact that if the solution existed, it would be a function like this. So we know that the function would be plotted as a graph like this. But what is a graph like this? A graph like this basically is a collection of points of this nature. Let's say we've got x here, and then we've got y here. These points, the coordinates of these points are simple: x, comma, f of x. In this case, y, which is f of x. So now if we collect all these points, normally we cannot collect all the infinite points for this graph, but we can sort of plot a few points or a sample of points and then connect them continuously like that, and they get a graph. From this idea, that's exactly where we start thinking of how we can get to a method or approach to solve the equation we were talking about numerically, which in this case is dy dx equals to y squared minus x squared. So to solve this equation over a small interval like this, before we get to the approach of the formula, let's first of all get the following ideas. We know that if we've got a function dy dx, like we've got y squared minus x squared, if you multiply both sides by dy here, what we actually get, we get dy equals to y squared minus x squared dx. Now, we should understand now here that dy, we're actually talking about the increment in y. And the dx, we're also talking about the increment in x. In other words, if we're at this point here and we say this is dx, which means if we're at x here, at this point here, we're going to have x plus increment in x. But now, what is this suggesting to us is that actually the increment in y is actually the product of the increment in x multiplied by the function. In other words, then, if we knew that the value of y here is this level, is at this level, y is at this level, and we knew the increment in y, that is this, at this point, then we can plot this point. Then what does that mean? In this case, let's suppose we didn't have this blue graph here. We would have a point x, y, which in this case I should mention that for a differential equation like this we solve numerically, you'll be given initial conditions in this form. For example, you can be told that y at 0 is equals to 1, which exactly means that, remember, 0 here is standing for x, which means then the graph of this function passes through 0, 1. So, but this formula here, if we could get the value of this function knowing y and x, then which means we can get the increment in y by just multiplying this value by dx. So now if we know the increment in y, then we'd have a new point here, which is going to be x plus change in x, comma, y plus increment in y, which is actually precisely f, the value of the function at x plus change in x. So once we've known this point now, and do exactly the same thing what we did with this point to get this one, we can actually go on and find the next point. So at the end of the day, we're going to have let's say a table of values where initially for x we've got x0, x1, which will be x0 plus increment in y, and then x2, which will be simply x1 plus increment in that, x3, and so on. So what does that mean? It means that when we are given these initial conditions, we should also maybe choose our increment, which we normally are going to denote by h, or increment in s, which are going to normally denote by h. And then using this kind of idea, we then initially would have y0 here. For y, we could have y0. For what we have done here using this formula here, we get this point. From this point, we'll get the next point, so which means we can get y1, y2, and y3. So once we have done this, then these points can now help us to plot the solution in a small interval. So that's where exactly we get the value of the function. So this discussion actually lands us at a situation whereby the next value, let's say we're given x0 and the y0. So now if we want y1, what we've seen is that we'll have y1 being y0 plus the increment in what? In y. So now once we got, let's say initially we're given x0 and y0, which actually means that the function passes through the point x0 comma y0, where you should understand that x0 is the value of initial value of independent variable, and the y0 is actually the value of the function at x0. Now according to what you have seen, then y1 would be y0 plus the increment in y, but the increment in y is precisely the increment in x multiplied by the value of the function at x0 comma y0. Now if we do that, if we do this for y2, you get exactly the same thing, that y2 would be equals to y1 plus the increment in x multiplied by the function. Now the function was initially evaluated at x0, y0. Now notice that we have got x2, which will be simply x0 plus increment in x. So now here the function will be evaluated at x1, y1. So continuing this process, you will see that when we get to the nth value, let's say n plus 1, we would basically need the nth value plus the increment in x multiplied by f evaluated at xn comma yn. In other words, you use the previous value y to find the next value. So when you continue this process, you basically obtain a formula which we write this way: y plus 1 equals to yn plus hf of xn comma yn. So this formula will simply give you a table of values whereby you will complete the row for x and the row for y, values which you can then plot on a system of coordinates, and the graph you are going to obtain would be y equals to f of x, which is an approximate numerical solution to the given differential equation. And this formula which we have just arrived at here is actually the first formula people are usually introduced to in as far as numerical solutions of differential equations are concerned, and this is called the Euler's formula. And this formula is what we're going to use to solve the first formula we're going to use to solve a differential equation using numerical methods. At this point, now that you've got the formula, I'll end here, and the next presentation will simply focus on using this formula to solve a differential equation. The most important thing here is, 1, numerical methods are going to be used over very small intervals. 2, you must be given initial conditions, like for example, let's say y0 and x0. Simple, what this means, this simply means that the graph you're looking for passes through x0 comma y0, which is the same thing as saying x0 comma f at x0. And a very important necessary, you must choose a step. A step is what I initially called an increment. In this case, the increment which I denoted delta x we're going to denote it here like in the formula as h. It can be anything from 0, let's say 0,1 or 0,01. So the finer the increment or the smaller the increment, the better approximation of the solution you are going to get. So with these three things, the initial conditions, the step, and the small interval over which you approximate the solution, those are the necessary things in order to engage this method of solving differential equation using numerical method. At this point, thank you for listening. The next presentation will focus on a particular example using Euler's method.